This is Introduction to Biology Chapter 1 and the Principles of Water Chapter 2. You're responsible for the material in Chapter 1. We won't be going over it in class unless you have questions, but you will be responsible for it on the test. Instead, we're going to begin with water. The first thing you need to know about water is that it is an electronegative molecule, which means that it has a strong attraction for the electrons that belong in other atoms or other molecules. It pulls those electrons, pulls those molecules toward it, creating strong bonds. If you are a non-polar molecule, then that means that you are not electronegative at all. You are neutral. The electrons that move throughout the molecule move equally, and so there is no charge. If you're looking at a polar molecule like water, one side is positive and one side is negative. The difference between the positive and negative side determines how strong or how polar the molecule is. Water is highly polar because of the size difference between the hydrogen and the oxygen atoms. If you follow an electron around, as it moves around the hydrogen, around the much larger oxygen, and around the small hydrogen, you can see that the electron spends more time circling the oxygen atom than it does the hydrogen. That means that the oxygen is negative while the hydrogen is positive. This polarity is what drives the properties of water. The other thing that's most important about water is that its ability to form hydrogen bonds. A hydrogen bond is an attraction between a hydrogen atom of one molecule and a negative atom in another molecule. If we're looking at water, we're looking at the hydrogen of one, the oxygen of another. That's what makes water stick together. That's what makes water be able to flow. If you look at another molecule, again, it's the hydrogen of one and a negative of the other. So, for example, in our picture, an organic molecule could be a sugar or a protein. This is what allows water to dissolve just about anything. And in the body, this is what allows water to bring nutrients into a cell and wastes out of a cell. Individual properties of water include its high specific heat. What this is how much energy it takes to get the water molecules to come apart, meaning at the hydrogen bonds. So what happens, say for example, you put a pot of water on the stove, and you wait and you wait and you wait, and then finally it begins to boil. The reason it took so long was because of this property of high specific heat. As the temperature comes from the stove into the water, the hydrogen bonds absorb that energy. They absorb it and absorb it and absorb it. Finally, when they can't absorb any more heat, they break apart. That first initial breaking of the hydrogen bonds is what allows water to go up 1 degree. Every additional set of bonds that break allow the temperature to go up. That's why it takes so long for water to boil. It absorbs so much energy before it can actually change in temperature. This is very important for both the environment and for the individual. In the environment, large bodies of water can absorb and store huge amounts of heat from the sun during the daytime and during the summer, but yet they only go up a few degrees. This is important because at night that heat is released, and so the night air is warmed. So during the day, you have heat being reduced as the water absorbs it, and at night you have the heat being added back to the environment. This keeps day and night temperatures from being so drastic. This is also why along coastal areas like where we live, we have milder climates than they do in the Midwest, where everything is controlled by the heat radiating from and into land. For living organisms, it's very important because we're composed almost entirely of water. All of the reactions in our cells happen in water. That means that every protein that is broken down, every energy molecule that is used, every sugar molecule that is created, creates heat. Considering how tiny a cell is, that energy, if it wasn't absorbed by the water, would build up very quickly and our cells would burn up. This is what specific heat does for each individual. Water also has a high heat of vaporization. This is related to specific heat. It's just a continuation. What means that it also requires lots of energy for water to go into a vapor, to a gas. This is important because for the individual, when you sweat or an animal pants, the heat that causes the water to evaporate comes from inside of the body, which means your body temperature is lowered and you're able to better maintain homeostasis. In the environment, it's basically the same as specific heat, except that in this case, we're talking about heat in the air evaporating water from the lake. As that happens, that air around the lake or around the ocean gets cooler. Heat is also used up when surface of leaves transpire, when they release water. That also gets evaporated and also cools the air. At night, all that water that was in the air condenses back to liquid, which releases heat back into the atmosphere, making night warmer. The combination of these two effects keeps our environment more stable, and we don't have the huge fluctuations that you would have, say, on Mars, where 300 degrees below zero at night and 300 degrees above zero during the day. Another property of water that is very important is that when it solidifies, it is actually less dense than when it was a liquid. Which means that also when you get solid water, it expands rather than contracts. Everything else on the planet contracts when it gets cold. What happens is as water cools, the molecules move slower and they move closer together. As they move closer together, the molecules have to rearrange because the negatives push away, the positives push away. So the negatives are attracted to the positives. When it does this and the molecules move closer and closer to each other, if you look at the picture, there's a little tiny space between where the positives would touch the negative oxygen. That creates a little pocket of air. That little pocket of air makes ice less dense. That's what makes it float. The fact that the molecules can't fit closely together because of that positive-negative shape is what makes water expand. This is important in the environment because in areas where the lakes and the ponds freeze, they freeze from the top down. If they froze from the bottom up, eventually, if it froze solid, the fish and other aquatic life would end up out in the air. In this case, it creates a cap. It freezes at the top and works its way down, protecting the aquatic life from the outside air and from the extremes in temperature. Finally, water is a good solvent, which means it dissolves everything. Water is called the universal solvent. This is important because that's what allows molecules of nutrients to move into the cell and wastes to move out of the cell, as I mentioned earlier. There are some things, however, that don't dissolve, and those are the non-polar molecules. Non-polar molecules do not dissolve because they don't have anything for the water molecules to attach to. Remember, a polar molecule has the positive of one end attached to the negative of the other. So what will happen in dissolving, the water molecules will surround the polar solute, the material that they're breaking apart, will surround it, attach to it, and basically pull them apart. If you have a non-polar molecule, there's no charge. There's nothing for water to stick to, and so they cannot be dissolved. Now, this translates into organization. Hydrophilic and hydrophobic. Hydrophilic molecules are charged molecules that are attracted to the hydrogen atoms in the water. Hydrophilic molecules are also polar, meaning they have one positive end and one negative end. Hydrophilic molecules dissolve easily in water, and what happens is, like we talked about, the hydrophilic properties, the positive and negative, they're surrounded by the positive and negative portions of the water molecules. They break them apart, attach to them, and that allows them to mix evenly within the water, which is dissolving. Hydrophobic molecules are non-polar, meaning they don't have a charge for the water to collect to or attract to. What happens is the water molecules surround these non-polar molecules in an attempt to find a way to break them apart. But since they can't, they just end up pushing those non-polar, those hydrophobic molecules together. And they end up clumping together. This is called non-polar exclusion. This is going to prove to be very important when we talk about cell membranes and what comes into the cell and what goes out of the cell. The last couple of properties we're going to talk about are cohesion and adhesion. Cohesion is water molecules attaching to one another. That would be the positive hydrogen attaching to the negative oxygen. What this does is create one thing that we know for sure and we see a lot, which is called surface tension. Surface tension is that skin that you see or you feel on the water. If you put your hand very lightly on water, you can feel the surface. That's surface tension. If you look at the picture of the bug, you can see where its feet are actually pushing down on the surface tension of the water. That's what keeps it from falling into the water itself. Cohesion, that attraction of water to itself, is what makes water fall in raindrops instead of individual water molecules. It's why water beads up and rolls off a freshly waxed car. It's what makes water flow rather than plop into a cup like bad milk. Adhesion is, in a sense, cohesion, except involving something other than water. It's the attraction between water and other polar molecules. Again, you have the hydrogen bonds of water and whatever polar material that you're looking at. This could be a paper towel. This is why when you put a paper towel in water, the water is attracted to it and attaches to the polar portions of the paper. The combination of cohesion and adhesion is called capillary action. This is what allows water to move up into a plant by way of the roots and the stems. What happens is water attaches to itself at the bottom of the roots, cohesion. Then as the water attaches to the root itself, you have adhesion, the polar water attached to the polar root. The cohesion of the water attached to the root and then attached to the water below it in the soil pushes it up. And then you have two molecules in the root attached to the root through capillary action, and it moves the water up. Similar to the picture of the straw. How small that straw is determining how far the capillary action works. And this is the end of chapter 2.